Hi, today we're going to talk about metathesis reactions, also known as double replacement. There's several types. We're going to start off with neutralization reactions. So we're talking primarily here acid-base reactions, Arrhenius acids and Arrhenius bases for the most part. When an acid reacts with a base, you produce water and a salt. And so the water comes from the hydrogen from the acid and the hydroxide from the base. And then the cation of the base and the anion of the acid make the salt. These are not redox reactions, so nothing is being oxidized nor reduced. Take a look, page 152, example 410. Read along. It says, predict the products of the reaction between hydroiodic acid and calcium hydroxide. Write balance formula units, total ionic and net ionic equations. So you'll be doing this exact same thing on your homework and on the test, where you write the complete equation, and then the ionic equation, and then the net ionic equation. Now, something to take a look at in that example, in our ionic equation, since both hydroiodic acid and calcium hydroxide are strong, we're going to show them dissociated, or in the case of the acid, ionized. So be careful with strong versus weak acids and bases. If it's a strong acid or base, it's shown completely dissociated or ionized. The products of that reaction are calcium iodide, which is soluble, so that is shown dissociated in our ionic equation, and then water is a liquid. And then take a look at the net ionic equation. This will always be the net ionic equation for the reaction between a strong acid and a strong base. Now be careful, students always think that this is the net ionic equation for any acid-base reaction. That is not true. Only strong acid, strong base, do we get that net ionic equation. Take a look at 411. This time we have a reaction between a weak acid, acetic acid, and a strong base. Notice in the ionic equation that acetic acid is not shown dissociated or ionized. That is because it is weak. We have to leave it that way. Potassium hydroxide is strong. We show dissociated. So again, take a look at that net ionic equation. It is not the same as example 410, where we have, remember, the substance in the ionic and net ionic equations will be shown in its predominant form. So for a weak acid, weak base, its predominant form is unionized. All right, take a look, page 163, do number 95A only, and then we'll compare results. I got a little lazy in the ionic and net ionic equations. I did not show states of matter. Make sure you do show states of matter. All of the ions are aqueous, and the water is liquid. So our spectator ions are chloride and barium. And again, this is a strong acid, strong base reaction. Therefore, the net ionic equation is H plus OH minus makes H2O. Take a look at letter B. We have sulfuric acid, which is a strong acid, and strontium hydroxide, which is a strong base. This reaction produces strontium sulfate and water. This reaction is unique for a couple reasons. One, it produces a precipitate. Strontium sulfate is insoluble. Your book says moderately soluble. Insoluble in water. The other more interesting thing is that for sulfuric acid, it's a diprotic acid, meaning it has two hydrogens. But it is only strong for the first ionization. So technically, and I've seen this wrong in a lot of places, when you write the ionization equation for sulfuric acid, it should look like this. A lot of times I've seen it written as 2H plus SO4 minus 2, which is incorrect. You do not produce 2 moles of hydrogen ions for every 1 mole of H2SO4. Again, it is only strong for that first ionization. So I'm not going to have you finish letter B because it gets a little bit tricky. On the left side, we have H plus and HSO4 minus, and we're not really going to have that on the right side. So you're likely not to see reactions like this that have sulfuric acid where you have to write the ionic and net ionic equations. Again, just keep in mind that this is how it ionizes, not 2H plus HSO4 minus. All right, go ahead and do letter C. I think you can do that one on your own. Actually, no, I got to walk you through that one too. A little bit different. Let's take a look. It says perchloric acid and aqueous ammonia. Now again, this one is different because our base is not a metal hydroxide, so it's not an Arrhenius base, as I pointed out in the previous examples. So this one's a little bit different. So let's do for this one, anytime you have a weak base such as ammonia, even if it's reacting with a strong acid or a weak acid, it doesn't really matter. We're going to do a Bronsted-Lowry type reaction. If you remember from Chem 1, Bronsted-Lowry acid is a proton donor, and a base is a proton acceptor. So what's going to happen here is the perchloric acid is going to donate its hydrogen ion to NH3, and that's going to make NH4+, and then the HClO4 is going to lose an H+ to turn into ClO4-. So here's what we end up with. So you do not end up with water this time. Sometimes aqueous ammonia is written as NH4OH, and then I guess in that case we would end up with water along with ammonium perchlorate. So just be careful with a weak base reaction and an acid. It's Bronsted-Lowry. We have a proton donor, proton acceptor. And then for our ionic and net ionic equations, perchloric acid is shown ionized. Ammonia is not, since it's weak. And then ammonium perchlorate is soluble, so it'll be shown dissociated in the ionic and net ionic equations. So be careful with that one. I think it says number 95. Let's skip that. We already did 95. Let's do 97. Let's start off with just letter A. Let's read it together. It says potassium hydroxide and hydrosulfuric acid. Again, this one's a little different because our base this time is strong and the acid is weak. This is an Arrhenius acid-base reaction, so you will be making water. Just be careful with that. Go ahead and pause the video, work on that, and then we'll compare answers. So here are our three equations. So notice I have shown potassium hydroxide as dissociated. Hydrosulfuric acid, that's a binary acid. Be careful with that versus sulfuric acid, which is ternary, is weak, and so we show that unionized. And then we have a spectator ion as potassium, and so we end up with our net ionic equation as shown. Again, make sure to include states of matter for every substance and make sure your equations are balanced. We're going to skip letter B. It's the same or very similar to letter A. Letter C, just take a look at that one. This time we have lead-2 hydroxide and hydrosulfuric acid. The only difference here is that lead-2 hydroxide is an insoluble hydroxide. So it is not going to be shown as dissociated. So keep it all together, both the acid and the base. Your products will be lead-2 sulfide and water. So I just want to point out the differences on that one. All right, take a look at number 101 on page 163. It says, write the balanced formula units, total ionic and net ionic equations for the reactions of an acid and base that will produce the indicated salt. So this time, you're given the name of the salt that forms, and you need to predict what acid would react to make that with what base. So we have lithium carbonate. So first question is, what base? So let's go back to the definition of a salt. A salt is a substance that contains the cation from a base and the anion from an acid. So question is, where does Li plus come from? What base will produce the lithium ion in the salt? That would be lithium hydroxide. Next question, what acid will furnish the carbonate ion when these react to produce this salt? That would be carbonic acid. So I'll let you go ahead and finish writing the ionic and net ionic equations. Go ahead and pause the video, please. Here we have it. Again, make sure all three of your equations are balanced and you have states of matter for every substance. So again, one more time, carbonic acid being a weak acid, we do not show as ionized, but rather as unionized, and that's why we get these equations. All right, let's skip ahead to the most common type of double replacement reaction known as a precipitation reaction. So as the name implies, these reactions produce a precipitate, which is an insoluble solid. So what we have here, we take two aqueous ionic compounds, so two ionic compounds that are in solutions, mix them together. You produce a precipitate, an insoluble substance, along with an aqueous compound, a soluble substance. So with this one, you need to be careful. Make sure to memorize the solubility rules so you know which of the products is the precipitate. Take a look on page 154 and 155. 413 at the bottom says, will a precipitate form when aqueous solutions of calcium nitrate and sodium chloride are mixed in reasonable concentrations? So be careful. Just because you're mixing two solutions does not mean that anything is going to happen. So let's look at what would be produced if a reaction did in fact occur. We get calcium chloride and sodium nitrate. So this time we get a double replacement reactions. Works for precipitation reactions and also some of the neutralization reactions we saw. So some compound AX in solution reacts with some other compound BY that's in solution. So A and B are going to trade. You make two different compounds. One of those likely to be insoluble in water, and the other is soluble. So let's look at what we have here. Is calcium chloride soluble or insoluble in water? Is sodium nitrate soluble or insoluble in water? Now think about the ionic and net ionic equations for this reaction. I pause because it's not a reaction. Everything is a spectator ion. Nothing happens. So this reaction does not occur. Please, please, please do not write a chemical equation for something that does not happen. So no reaction. Can't have a reaction when everything is a spectator ion. Now if you look at 414 on the next page, we have calcium chloride and potassium phosphate. This time you're going to produce a precipitate of calcium phosphate. Therefore a reaction does occur. Take a look at the ionic and more importantly the net ionic equation. Your net ionic equation always includes the ions that react to produce the precipitate and nothing else. All right, go ahead and answer number 107, all parts of it, please. Pause the video while you do that. All right, here are the answers. Lead 2 sulfate is insoluble, so it would be shown undissociated, not broken apart, not separated as ions. Sodium acetate is soluble. It would be shown dissociated in your ionic equation. Letter C, sodium carbonate, also is soluble, so dissociated. Letter D, manganese 2 sulfide, insoluble in water. Therefore, it would be shown as undissociated. And BaCl2, barium chloride, letter E, soluble, it will be shown dissociated. All right, go ahead and take a look at number 113. Go ahead and pause the video while you work on that. Again, write the overall equation, the ionic equation, and the net ionic equation for that reaction. Pause the video. All right, so our products are potassium nitrate and barium carbonates. One of those, hopefully, is insoluble in water. Is potassium nitrate soluble or insoluble? It is soluble. All alkali compounds are soluble. All nitrates are soluble. Barium carbonate, soluble or insoluble? Most carbonates are insoluble. There are some exceptions. Those exceptions are the group 1s and ammonium compounds. This one is not soluble. Be careful here. S does not mean soluble. S, in fact, means insoluble. Go ahead and pause if you haven't already written the ionic and net ionic equations. And there you have it. Again, make sure all of your equations are balanced and they all include states of matter for each substance. All the ions are aqueous. Barium carbonate is a solid in all three equations. That concludes this lesson. Just looking ahead, next up we have the gas formation reactions. which are double replacement type reactions. These give students the most trouble, so I think we'll hold off on this until the next lesson. Let us focus on the other ones first. So thanks for watching, and we'll see you in class.